Okay, good afternoon, everybody. Welcome to this webinar. I see there are still people entering, but I propose we start because I think we will need the full hour. My name is Hans Mol. I'm from Wageningen Food Safety Research, and I'm the task lead of task 9.3 in PARC. And this is the first webinar in a series of webinars that is organized together with Carla Trindade Costa from task 9.4 and us. And the speakers of today will be Petr Kukučka and Jan Kuta from RECETOX in Brno. And I will first do a short introduction before they start. Can you please move the slide, Petr? Yeah, the next one. Yeah, so PARC, for those who are not familiar with PARC, PARC stands for the Partnership of the Assessment of Risk of Chemicals. And it's a huge European partnership where most member states are involved, many institutions. And as you can read here, the aim is to develop next generation chemical risk assessment. Very important aspect of that are monitoring of chemicals in environment, in humans, in food. And also hazard assessment. And in that respect, there are a lot of laboratory tests done. And the main aim of task 9.3 is to work towards a harmonized quality assurance and quality control in laboratory testing. So it's a transversal task within PARC. And the goal is to ensure that the data that are used and the data that are generated within PARC are consistent and comparable across the different chemical matrix and even technique domains. Of course, as much as possible, there are differences, but we try to harmonize as much as possible. Within this task, we have certain deliverable. These are guidance documents, and first guidance documents has been released last year. And with this webinar, that's part of our dissemination strategy to inform you about the outcome that we had published in this guidance document. Of course, this guidance document was not created by just a few people. There were over 80 contributors from 13 countries and 29 institutions who contributed to this. And next slide. So within this task, we have different working groups. The main focus is on quantitative analysis. There's different working groups dealing with the pre-analytical phase, so the sampling, comparability of laboratories, producing results, and on the reporting and acceptability. But for today, the main focus will be on performance criteria. Next slide. So this is the very brief outline of the guidance document. For those who are interested, you can find and download this document on the PARC website under deliverables. This document has been primarily generated for laboratory staff, so people actually doing the analysis and reporting the results, but it's also very useful as a background document for users of the data. Of course, there's a lot of QA, QC type of procedures already available. This is dedicated to what is being done within PARC, and whenever there are already international guidance documents that are commonly accepted in a certain domain or subdomain, or whenever there's even EU legislation, then of course that will take preference over this guidance. As I mentioned, it's about quantitative analysis. We go for best practices. What we provide here are the minimum requirements that quantitative analysis should comply with. And we try to keep it pragmatic as much as possible, so no complicated statistics, in order to encourage the actual use. And as mentioned today, it will be about performance criteria. And now I hand over to Petr and Jan.
Thank you, Hans, for a very nice introduction. And let me continue with the specific topic for today. So as Hans mentioned, our aim today is about the method performance parameters, and that we set up some minimum criteria for the method performance parameters. You know that in the quantitative analysis, there are various variables and things that you should be checking and preparing. So we have the common list of parameters that you usually are performing during validation of a method or a development of a method. And they include both of the things of accuracy, bias, identification, the measurement range, trueness, and everything, and matrix effects. And we're gonna today touch upon some of these specific things because many of the things are quite often clear. There are existing guidances, but typically they are for compliance or regulatory domain, which don't have to be always completely acceptable for the monitoring purposes, especially in terms of detection limits or quantitation limits quite often. So let me start briefly with the method performance criteria. You know that as I said, some of them do exist, but we are also aiming to set up performance criteria for human biomonitoring methods. And for that, there is so far none really found. So anything that would be telling you what should be your reporting limits, what should be your calibration range, and so on for the range of compounds does not much exist. There are some generic and large ones, but they do exist for pesticides or for pharmaceuticals usually, or there are some generic guidances that speak about quality in laboratory practice. So we got these, and those are quite often used in many of the compliance laboratories. But then there exist specifics for a specific, let's say, analyte or a food domain or a pharmaceutical domain, and they are mostly suited as being generic, so not much used for the monitoring purposes. To complete this introduction of the performance criteria, we have some of them that exist, but we have some mostly for the environment, for water quality, soil quality, and so on, food and feed safety, pharmaceuticals, and material compliance. But they usually speak about the maximum limits allowed, and quite often you have regulatory criteria on a method reporting limit. So anything that is below, you don't have to report, basically. But for the laboratories performing these testing and methods, they definitely can analyze concentrations lower than this one, but do not report. And this is what we want to stress and suggest use within the PARC and within monitoring projects, because this is more important for risk assessment. In risk assessment, the risk assessor is usually very happy for any reliable information. And if you provide information on a method reporting limit, which can be 10 or 20 times higher than your quantitation limits, which has low uncertainty, why shouldn't you be reporting your LOD and LOQ? And why are you still reporting the method reporting limit? And that's what we want to stress in this one. So when creating also the PARC guidance, we wanted to set up harmonized definitions and the minimum criteria, which will be fit for purpose for the studies and for the monitoring mostly. It doesn't have to be regulatory. Anything that is more stricter or higher can be still used. But what we want to achieve is for the participants and basically for the reporting to report data that can be used. Because, you know, if you have statistical analysis in risk assessment and you have some non-detects, if you put it up, you sometimes do imputation. So you either divide the provided LOD or whatever by the square root or the division or something like that, but this still will definitely in many cases cut off a lot of the data, which could still be used and still could be seen. So that's what we want to support, to report really concentrations which are above your quantitation limits, but the quantitation limits should be set with a specific uncertainty. And I hand over to Jan to continue with the presentation.
So I will start with the method performance parameters, how we set it in our guidance document. Firstly, we will talk about the detection limits, LOD, quantification limits, LOQ, and some criteria for identification of the analytes in certain metrics. I have to say that LOD and LOQ, those estimations can be quite messy because the methods, how you can estimate the LOD and LOQ, there's a lot of them. And it also depends particularly on each analytical techniques, how the data are provided, how the signal, it looks like, you know, whether the signal is somehow smoothed or not. So it has some consequences. And the main problem is that the LODs and LOQs are not consistent or not comparable between the labs and the studies. And once, for example, you have some labs that are generating a lot of data, there are already left sensors compared to another lab which is generating data with different LODs, that you have a problem with interpretation. So basically, limit of detection, it's defined as the lowest concentration of analyte in the sample that can be reliably detected, translated to some common language. So it's the lowest concentration that you can somehow distinguish from the, for example, signal noise, or from set of the blanks or something like that. Actually, for practical reason, we try to keep it practical. And, most of the data generated in PARC will be probably by the combination of chromatography and mass spectrometry. For organic analysis, or in case of elemental analysis, will be probably ICP-MS or other technique of atomic spectrometry. So we identified two situations. And the first thing is, if you have time resolved data from chromatography and procedural blanks which are free of the analytes, then we will use the signal to noise ratio for estimation of LOD. The second situation is if you have positive blanks, or you have some kind of signal which is not time resolved, as for example ICP-MS, that you have counts per second, it's a number. So then you will use that statistical approach, and the LOD will be calculated on the average blank concentration and its variability, so standard deviation. Yeah. And please, that's your...
Yes. So when speaking about the chromatographic data, you have some signal that continues within a time. So quite often you have some background, you have definitely the first, mostly mass spectrometry. In the end, you have a multiplier which provides you with the electric current which you measure and record a signal. So the signal always has some baseline, and definitely it is not a smooth line, because, well, we get measurements in very low power current ranges, so there's definitely gonna be some noise. The noise can be either coming from the instrument, which is the electrical noise, or really, since we quite often in the chromatographic system injected a solvent or the sample in some solvent and matrix, we can have the chemical noise. That doesn't matter at this moment, but the important thing is how shall we define the noise? Because, well, the noise line and the basically which creates the baseline is gonna be at some specific level that is there. So shall we take the noise which is the lowest point in the noise range, or shall we calculate the noise really from the 0, which is the highest one, and which time region shall we select for the noise? Because sometimes you can have other peaks in a specific region, apart from your expected retention time where the compound is eluting. The other thing is, how do we deal with the noisy signal? Quite often what we do is we apply some smoothing. So what is the smoothing algorithm? Is it too strong or too weak? And how does it calculate with the electrical or chemical noise? Because the chemical noise usually is a bit wider in terms of time. The electrical noise is really just the scattering that is there from point to point. Then the other thing is also, how shall we define our signal? Shall we take from the lowest point in the baseline, or shall we take it from 0 or somewhere from average? And one important thing is, what do we use for the calculation of signal to noise? Whether we calculate it on the real sample, where we got chemical background, that means some matrix, or shall we take the standard, which is usually matrix free? And then we have also a situation where there are some techniques that can produce, let's say, 0 noise, because at low levels, you don't get any signal at all for whatever reasons. For instance, in the orbit traps, because there it is given by the data amount generated. So something below a specific signal is not recorded at all. So what do you do then? So we've set up a few examples where we see how noise can be calculated and how does it affect really the calculated concentration. Because when we say that we should be calculating the LOD on the signal to noise ratio of 3, And looking at the chromatogram here to the left, and the upper part is unsmoothed, we can see even calculated signal to noise with the signal region and the noise region somewhere around. That once we first, when we apply smoothing, because the chromatogram is much nicer and smoother, of course, the signal to noise did increase about 3 times. And this similar thing will happen definitely with your standard if we apply the same situation. So that's one thing. Where do we take it? The other thing is, how does it really look in our real sample? You see also here, if we should calculate the LOD on the unsmooth signal, where we have a specific concentration given, and the signal to noise range was 24, then the detection limit calculated was 0.05 microgram per milliliter. On the other hand, once we smooth it, we get 3 times lower. So we are getting somewhere 0.015. So which one is true? I'm not saying that one of them is wrong or one of them is right. I'm just wanting to stress that the smoothing will definitely affect your situation, and it is about also the expertise of the analyst, of the person, to decide which is the best. So we definitely do allow some smoothing in reasonable range. Of course, the word reasonable is quite soft, but basically what we need is to apply really slight smoothing that will get you rid of most of the electrical noise, but the chemical noise, as you see the peaks over here and here, will still remain. So they are still there. They are not smoothed and not removed. And similar situation in the region over here. Then it's still applicable and usable. Now the real situation also, when we got matrix inside, what would be the signal to noise ratios? Signal to noise ratios. You see those calculated for the same compound in a few different extracts of different food products, or basically seeds and cereals. So you see that the signal to noise ratio does change, even though we have basically spiked the matrix with the same amount, so we have the same concentration. And in the end, we're going to calculate the LOD is going to be specific for the specific matrix. We must also stress that the LOD is estimation, and it's something that you can really detect and say that, okay, this compound is definitely present. We don't know what exactly is the amount, but we can definitely distinguish with more than 95% probability it's not coming from the blank, it's not a background. So that's how we are treating LODs. Quite often, going back to the introduction where we have, let's say, compliance and regulatory laboratories, they have some method reporting limits which are set up much higher. So even those concentration, they would not be reported as below reporting limit. And it is very convenient, of course, for the laboratory to set up their LOD quite high, because that can be achieved and kept for quite a long time from now on. What we want to support is to provide the real experimental LODs that are coming with the batch of the samples and the batch of the results. Moving further information that, as I was mentioning before, very sometimes at low concentrations you cannot have, don't need to have a specific signal at all, which can be a case of high resolution analysis, for instance, on the Orbitraps. Then we set up the parameter that the LOD is the concentration where we have at least 5 consecutive scans. And you can see the presentation here at the chromatograms with the rising concentration from the left to the right. So at the lower one, 0.5 nanogram per milliliter, we get only 3 scans. At 1, we got those 5 scans. So we can say that the LOD in this case would be 1 nanogram per milliliter. So to summarize, or to speak about our guidance for the detection limits, we have some best practices. So use samples that undergo the same procedure. That includes the extraction and cleanup. Samples should contain the analyte at a specific level, which could be at least 10 times below the expected LOD. use multiple samples, because in this case we have got the variation where basically we're gonna statistically calculate the relative standard deviation of the blank signal. With the chromatography mass-based techniques, we have also to take into account with the quantifier ion, because sometimes, well, many cases you have a qualifier, which is the other ion that is good for your identification, but we calculate only using the quantifier, not the qualifier, because that can be quite low in some cases. And then the LOD is the signal concentration corresponding to signal-to-noise ratio of 3. And ideally, we should be taking the signal from the average baseline, and peak is on the top of the peak, and the noise should be calculated as, and the ratio should be calculated as peak to peak. You know, there are some other algorithms like root mean square, which somehow smooth the noise region, but we suggest that peak to peak is much better. It definitely provides you with a bit worse value for the LOD, but that one is definitely much more realistic. And we should have at least 8 points per peak. That is common chromatography, so that we got at least 2 or 3 points at the top of the peak, if this is really nice and Gaussian, so that we have very good resolution of the data. And smoothing, as mentioned, can be done, but not too strong. And of course, if you select this sample and you calculate that the signal-to-noise ratio is greater than 30, then you have calculated even concentration which is higher above quantitation limits. You should repeat with lower concentration to really determine the LOD.
So the situation, it's completely different once you have positive blanks. You know, it can happen in metal analysis, you over have positive blanks, and for some big kettle organic analytes, like for example PAHs or trifluoroacetic acid, you know, it's almost everywhere. So you have positive blanks. When you have positive blanks, you should calculate the LOD, which is based on the variability of the concentration of analyte in the blanks. So we propose to use the average concentration of the blank plus free standard deviation across the blanks in case that the RSD of the blank analysis is higher than 25%. Once you have a stable blanks with variability less than 25%, you can subtract the average blank from the samples, and then you can calculate the LOD as free standard deviation of concentration of analyte in the blanks. So, and now we have some examples. The case 1 represents the situation where you have all the blanks are positive, but the variability is quite high. Its RSD is 59%. Then the LOD is calculated as average of the blanks plus free standard deviation, which result in this number. Case B represents the situation that you have very stable blanks with low variability, where RSD is 14%, then you can subtract the average of the blank from the samples and calculate LOD as free standard deviation, which is here. The case C represents the situation that you still have some positive blanks with frequency higher than 30%. Then you again follow the same rule that you calculate firstly you will check the RSD, and which is higher than 25%. So you will calculate LOD as average plus free standard deviation. And the last case represents situation that you have some of the positive blanks, but the frequency lower than 30%. So you will follow the rules, what was mentioned by Petr, by defining LOD from signal to noise, but you should carefully check the blanks with every analytical sequence if you don't have a bigger portion of the positive blanks. So now to summarize, there is a decision tree. So you have an analyte present in less than 30%, then you follow the signal-to ratio for calculation LODs. If you have more than 30% positive blanks, then you will look on the variability, so relative standard deviation across the blank series, which is less than 25%. You can subtract the background and calculate it as free standard deviation. If it's more than 25%, you have to count average of the blank together with the free standard deviations. So now quantification limit, just general definition, it's lowest level at which the performance is acceptable for typical application. Like typical definitions usually, how to say, contain some magical number, which is factor 10. So 10 times standard deviation or signal to noise ratio, which is equal to 10. But in PARC guideline, we decided to go more into the like validation. So it's the lowest concentration where the criteria for the trueness and precision are like met. So just translated to the common language is the lowest concentration that you can just show that the method is enough performed for our purposes. Yeah. Just the information that our guidance definition, it's how to say close on in line with Eurachem. And from a practical point of view, we decided that you will start with the LOD using our PARC guidelines, that you will estimate some possible LOQ, for example, by multiplying standard deviation by factor 10 or for signal to noise. Then you do a validation on that level. And if you met the criteria for trueness and precision, so you are fine. If not, you have to go high in the concentration and find the level what is working. Yeah. And yeah, it's for you.
So this would be about the quantitation limits. Now we are switching into another parameter important, which is identification. In the chromatographic and mass-based techniques, or basically time-resolved techniques, we have definitely compounds eluting at specific times, so we get retention time. And this is definitely one of the points that has to be matched for the correct identification. You have the sample and you have sometimes reference or standard, and you compare definitely the retention time with the standard. Then in the mass-based techniques or mass spectrometry-based techniques, you have definitely the spectra. And in the spectrum of your compound, if you are obtaining the data in the full range, so doing full scan, you will have definitely the molecular peaks or the highest abundant peak, and then some lower abundant peaks, which definitely still below to your compound. So you should be selecting at least one of those lower intensities, typically called qualifiers, that should be involved in this one. And the set ratio parameter of your qualifier against your main peak, which in this case is used for the quantitation, so we can call it quantifier, and evaluate the ratio in the measurements of your real samples in the end. So we are matching retention time and the mass, or MZ in this case. And we've got a situation where we have the peak, which elutes at these 5.8 minutes, something, and another one on the right-hand side, we have an extracted chromatogram from the same compounds, but a different mass, because the first one is at, I can see it as it's too small at the moment for me. But yeah, definitely the other one is a bit different mass than the left one. So this is the qualifier. And selectivity and sensitivity of ions can differ. In the chromatograms on the left, you can see that also the absolute response is changing, where we have the absolute response over here somewhere, which is much higher than the other one. And of course, you have much more peaks on the left one, where the signal is more noisy and the instrument basically is more sensitive to anything. So it records much more of the situation. And what we set up in our PARC guidance is that the criteria for the retention time and the ion ratio of two ions based on the either extracted ion chromatograms or on the comparison. If you do targeted analysis and you already set at the beginning your MRMs or ions that you are recording, so at least have one qualifier to your quantifier. This is summarized in the table here. So that the retention time should be somewhere within the relative retention time, very close in the range. So we allow, let's say, 0.10 minutes, which is about 6 seconds of the retention standards, or you can have for the relative retention time. Relative retention time can be also the retention time of your compound related to an internal standard. In many cases in chromatographic techniques, you observe quite often shifts in the retention times, mostly due to matrix or whatever other reasons. So how you overcome this situation? Quite often you use some internal standards which is either not present in the matrix or you have it labeled in a specific way, like isotopically labeled. And of course, shift of the retention times on this one and your compound of interest are typically in the same direction. So relative retention time works very nice in this case. And then for the MS measurement, if we have unit mass resolution, then the ratio is that the qualifier should also be at least signal to noise higher than 3. If there are some compounds where the qualifier is always low, we can select at least some relative qualifier, which could be either protonated or isotopically labeled. Let's say many compounds are carbon-based, so once you have too many carbons, at least 10, then there's much higher chance that at least one of them will be carbon-13, and we have a mass on that one 1 Dalton higher. In some cases, you can have protonation, so that can be used as well. Or adducts. And in the accurate mass, we should have the 2 ions with mass accuracy lower than 5 ppm for the consecutive scans. And there are the specific examples. Further details are listed in the PARC guidance document. But basically what we mean to say, proper identification is met if the retention time is okay, not shifting too much, and you have the correct ratio of your qualifier versus your quantification ion. Now for another example for the identification, where we can have measurements of, let's say, 3 PBA in an urine extract, and we have a quantitation I transition in this case to the mass 213 to 93, and we would select from the standard that we definitely see in a standard as signal on 213 to 169. But in the real sample, we see that this transition is very noisy and basically we cannot see the peak anymore. So in this case, we can use, as mentioned before, use the specific like carbon-13 isotope inside. So M+1 in this case. So instead of 213, we have the 214. So that's still acceptable. Because this happens especially if you are analyzing really small molecules that don't fragment too much or are usually only monoisotopic, and you will not see much strong fragmentation where you could take a fragment to be your true qualifier for the compound of interest. So we still allow that pseudo-isotopic peaks or isotopic peaks can be used as an additional qualifier. Now, what is important is that the ion ratio should be calculated as the low to high. So sometimes, in some cases, you could have a situation where you select that the lower abundant ion is going to be your quantifier for the reason that you want to be definitely sure that you are quantifying correctly. And basically do not overestimate maybe some cases where there could be an interference, for instance, on the higher abundant mass. But still, you should be calculating the range, the ratio as the lower to the higher. So always the usually qualifier against the quantifier. And this is the situation where we set up the criteria that the ratio of the qualifier against quantifier should not be larger than, let's say, 30%. If we calculate the situation as low to high, then we are definitely not meeting the tolerance range because the ratio has changed in this case, where it should be correctly 10%. But in the real samples, we have 13% ratio of the qualifier against quantifier. And if we calculate it as divided by the high to low, then we get a bit different situation that differs only by 26%. So we are stricter in this way, in this case. Now just comparison of various other techniques. So for instance, there's a Commission regulation for veterinary drugs, which gives you information about correct identification if you are meeting different points. So it defines the quality of identification by basically the means of what technique you are using. So if you are using high resolution MS and you have product ion, we have 2.5 points. If you have only the main ion, you have 1.5 points, and in the other situation is here listed together. And there is some, because this is a regulatory situation, so they are much more strict on the identification. So for instance, for the prohibited and banned compounds, you have to have really very proper identification. So you should reach, using the techniques and things, the score at least 5. In just for the reporting, you have to reach much lower criteria. And for many people who do non-target screening, you are definitely aware of the Szymanski level, which Eva Szymanski published already more than 10 years ago, which goes to the identification of the compounds related to spectral matching and libraries. So we got level 1 up to level 5 identification, where the level 1 is just you have the exact mass, and the level 5 is you have the confirmed structure compared to the reference standards. In this case, with the techniques, they don't speak about retention times or ratio, they just speak that the spectral match should be fine. And we in the PARC define that retention time should be, well, has to be used for identification as well in the chromatographic techniques.
In case of elemental analysis, it's situation different because we don't have any strict criteria for the identification of the analytes, but you should carefully select, for example, the isotopes what we are using for quantifying, which are not really affected by the spectral interferences, or use multiple isotopes or multiple wavelengths in case of optical emission ICP, for example. And of course, use some system for suppression of spectral interferences like collision reaction gases, or the spectrometers with higher resolution. So now the last slide about the LOQ from point of requirements, because we have some analytical requirement. We were already talking about it for the last 30 minutes, but we also have to think about the uses of the data, because all of the LOQs and LOQs should be fit for person. It means that should be low enough that the data we are generating can answer the scientific question, to avoid to have a lot of data left censored. So ideally, that should be some agreement between the study owner and the analytical labs to have some minimal, for example, LOQ, which will be feasible or technical somehow feasible and low enough to answer those questions. Of course, sometimes it's quite problematic, especially in case that you don't have too much information about the levels in the, population. So you should be as low as possible. Now we will talk about the calibration and matrix effect and some other things which can affect the quantification. Related to the calibration, we choose back-calculated concentration as the criteria for the validity of the calibration curve. From our point, it's much better than, for example, R-squares, because we have two nice examples here. On the left side, you have nice calibration curve with R-square 0.99999. But if you calculate the back-calculated concentration, you have the concentration in your standards, and this is back-calculated by the linear regression. And you can see that you have very high deviation for the first calibration point. Then the calibration curve is not valid for concentration below 0.25. Microgram liters or whatever. The second example shows the calibration, which optically looks much worse, but the back calculated concentrations are across whole working range for less than 20%. So this calibration can be used for analysis of organic analytes. For elements, we are much more strict, and we set it as 10%. Yeah. So the message is don't over-rely on R squeezers. What can influence also the result? It's like combination of matrix effects and the signal drift. Here is some example of the analysis of urine by ICP-MS, and this is recovery from the internal standards. Each point represents each sample, and like the distance between those points can be addressed by the matrix effect. You know, that red line represents the signal drift, which can be associated, for example, with the deposition of the matrix on the cones or on ion optics. And you also have some, it looks like signal spikes in those charts, and it's associated with the analysis of blanks, which doesn't contain the matrix. So we can see that the blanks free of matrix have completely different matrix effect. And how we can deal with that is the proper calibration strategy. There are several ways how we can calibrate our instruments. You know, basically, you can have external calibration without internal standardization, which is quite problematic because it's not easy to match the matrix itself, and you cannot compensate the signal drift. Then we have standard addition method, which is not really suitable for routine analysis because it's very time demanding. So basically, two methods are used, and that's external calibration with internal standards, ideally isotopically labeled, or isotopic dilution. Of course, it depends also on the cost and availability of isotopic labeled standards. But yeah, it's if you can choose that, it's always better to choose some isotopic labeled standards. Yeah.
Talking about the standards and other things, how we set up the method performance, we quite often speak about the accuracy, which in our case, accuracy is a combination of trueness and precision. So how true is your result and how precise you are. You have some types of errors, and there's theories and definition, and not only theories, but really whole statistical science about how errors tend to propagate and how you can calculate the whole error of your measurement using the different increments from the devices and things that you are using, because each of them is usually defined with a specific standard deviation or some error. And once you combine it together, you can calculate the total error. You can do this example. Or quite often what we do, and what is much more simple, we take the whole procedure and do parallel samples, at least, let's say 5 or 10 of them, and can do some statistical evaluation of the results afterwards. The accuracy is basically the closeness of agreement between a test result and a true value. And it's, as said before, combines the trueness, so how close are we to the strict concentration, and the precision, which is basically how scattered is our results. So what is our RSD in the most case. So the true value can be taken either as the true value from a certified reference material. Usually, if you have that one available, you have very good thing, because well, you can something that you can rely on. If it's not available, then you provide some reference material which is suitably homogeneous and stable and has at least a consensus value, maybe provided from inter-laboratory study or proficiency testing. A certified reference material comes up with a certificate, and it has been already certified within many laboratories usually. Sometimes that one is not, reference material cannot be always available. So in this case, we determine the trueness based on recovery, which can be the spiked internal sample, either spiked matrix or some spiked, basically typically the spiked matrix in the lab. And that will be your true value. So we have a situation, for instance, where we calculate the trueness by recovery. In a case one where we have no internal standard and extract our sample, and we know that the yield of my analyte is 50%, but we also observe matrix effect, which provides the 40% enhancement of the signal. So if we spike 100 milligrams into the sample, what we see in the end is gonna be what level? Shall we see a 50% signal? But talking about, because we know that our yield is 50%, but speaking about that, we have 40% matrix effect enhancement is gonna be increasing. So we're gonna be seeing 70%. And this is our apparent recovery in this case, and we can take it as the true value. This is our consensus that in PARC, in the guidance, we can use apparent recovery as the trueness-defined recovery. Of course, this has to be statistically proven, so cannot be only a one-time measurement, but in a series of rounds. Basically, it's a systematic error, a systematic bias that is there. You can calculate it and you can use it. And in this case, if we should calculate the trueness as bias, the bias is 30% because we spiked, let's say, those 100 milligrams, we got 50 milligrams back, but only given the matrix effect which enhanced the signal corresponds to a 70 milligram in a standard. So we are at 30% bias. In a second case, if we add isotopically labeled standard into my sample, so that should behave during the sample preparation exactly the same as my analyte. In the best case scenario, still the extraction yield is 50%, and we have some enhancement in the chromatography. Let's say about those 40% again. What would be my recovery? So we know that the absolute recovery is 50%, but using the compensation of the internal standards, the apparent recovery is going to be 100% because we set up its concentration at the beginning, and this is what the calculated concentration should be at the end, even though we have only 50% yield, but 40% enhancement. So in this case, the trueness expressed as bias is 0%, so we are getting everything correctly. That is the ideal case. Of course, it doesn't have to work always exactly the same, but in many cases and vast majority of cases, this works very nice. So we suggest, of course, to use isotopically labeled standards if available. Then recovery definitions are defined by that. The absolute recovery noted here is really the extraction yield of my standard, while our apparent recovery can be different because that takes into account the matrix effect. And if we have the signal enhancement, then of course the recovery can be higher. On the other hand, you can have suppression of the signal. In this case, the apparent recovery will be much lower. When speaking in terms of PARC, the trueness established for recovery, we applied the criterion to the apparent recovery. Now, trueness, of course, we should be testing it at the replicates and doing the replicates in multiple days. Now speaking about the precision, basically. So our precision is that at each level, we should have the average trueness lower than 25%, and that corresponds to the recovery of 75 to 125%. For precision,
No, maybe I should follow. Okay, so now we are talking about the precision. So actually, it means how analysis on individual samples are close to each other, or analysis of one sample, individual analysis of one sample are close to the other. It's presented by the relative standard deviation, which can be either like intraday repeatability or interday. It's called intermediate precision, or there is also relative standard deviation, which is connected to reproducibility. It means if you have the same sample, which is given to several labs, and they are analyzing the samples with the same or equivalent method, and you will get the RSD from the proficiency testing. So in our case, like PARC, the intraday RSD, so repeatability should be done on let's at least 5 replicates within the one analytical sequence. So you have to test the reparability on the anticipated LOQ, then on the level which is from 5 to 10 times higher than LOQ, and then ideally on the concentration when you expect most of the samples. So intermediate precision, so interdate precision should be done at least on 3, preferably 5 working days with 5 different analytical sequences, again on the same levels, so LOQ 5 to 10 times LOQ, and ideally in the concentration where you expect most of the samples. Yeah, and finally, just to summarize things about the trueness, precision, and accuracy, I will just shorten it. So I will just conclude that the trueness should be between 75 and 125%. RSD, intraday and interday should be less than 25%. And the last thing what I have to say, it's if your lab is participating in the alignment studies, PARC alignment studies, you should be involved in the proficiency testing. And currently, our criteria that you have passed the proficiency testing is that your deviation from the central value or expert-based value is not higher than 50%. And that's all from our side. And
thank you very much, especially Petr and Jan, and have a nice weekend.
Yeah, thanks all the attendants. Thank you, Kyla and Hans, for hosting us, and have a nice weekend at each of you.
thank you.
Thank you. Bye-bye.